Hi, I'm Ludwig Wilhelm. Welcome to my presentation, Scrappy, using scrap material as infill to make fabrication more sustainable. In FDM 3D printing, material is deposited sparsely within the volume of the printed model to provide critical internal support structures. This infill provides mechanical strength and in many cases makes a successful print possible in the first place. This internal support, however, comes at a cost of increased printing times, higher material usage, and higher energy consumption. Meanwhile, our formative interviews found that makers tend to store a variety of scrap objects, often for extended periods of time. When printing the scraper tool, the print on the left without infill fails. The print on the right with infill succeeds, but it takes much longer to complete. Ideally, we would like to benefit from internal support structures without having to produce them expensively. Regarding related work, for prototyping applications in which the mechanical strength of the models is not important, prior work such as wireprint has already achieved printing entirely without infill. Infill optimization for additive manufacturing uses topology optimization to adjust the layout of the infill. For example, to withstand expected forces using the least amount of material. Our system follows a different approach and can be used in conjunction with infill optimization for even greater material savings. In Encore, models are extended or enhanced by printing on top of existing geometry. Our system makes use of the same idea, but for a different purpose. Scrappy allows users to repurpose scrap, like failed prints, early prototypes, or just common household scrap objects, to save time and material when 3D printing. To do so, scrap objects fulfill the role of infill material. They are inserted by hand during fabrication. This simple but effective technique is made possible only via the combination of each of the different parts of our system. Firstly, since this technique relies on having a collection of available scrap objects, our system includes a web-based scrap library that tracks available scrap and offers a variety of options to generate meshes for new scrap objects. Our system, for example, includes mesh generators for a number of common household disposables, such as coffee cups. Scrappy also integrates into the existing CAD process. To do so, we provide a Fusion 360 add-in. Suggestions for scrap inclusions are presented during the modeling process. They are ranked by how much infill they would replace. These suggestions can also be loaded directly into the current model. The suggestions are provided by our Insertion engine. The Insertion engine is based on an adaptation of Jacobson's generalized Matryoshka algorithm. It determines how scrap objects could be inserted into a given model. To do so, the algorithm uses ray tracing along the printing direction to identify outline collisions for candidate insertions. It gradually increases the scale of the scrap object to determine at which scale collisions first occur. A particle swarm optimization then uses this data to quickly find alignments at which a scrap model can be inserted at full scale without colliding with the outline of the outer model. Once a favorable alignment is found, the algorithm computes a mesh of the resulting scrap cavity. Finally, our system also makes adjustments to the slicing process to avoid generating internal walls around the scrap cavity. During testing, using our system reduced both printing time and material usage by up to roughly 50%. We found that Scrappy works with a variety of materials, such as plastics, metal, wood, and stone. Scrappy integrates repurposing scrap objects as infill into the existing CAD workflow to make printing faster, more affordable, and ultimately more sustainable. If you own an FDM 3D printer, you already have everything you need to make use of our system. You can download the source code at bit.ly/scrappykai2021. Thank you.